All right, here we go. And so this is, again, a bit of review from last time where we're looking at the deformations of this spherical shell as we have the different orbitals. So this is the electron wave function. So the electron wave function is in 3 dimensions, and this is how that spherical electron cloud is oscillating. So we've done the s orbital on the left, the p orbital in the middle, and the far right is an example of a d orbital. So we have some expansions on the top and bottom and contractions in the middle. And so when we draw these, they look like this. We sort of draw these lobes where the motion is. And so it looks like this crisscross pattern, but we're just trying to show in this circle, the top is squeezing out while the middle is compressing in. And sometime later it squishes this way. So it's doing this. And so when we draw those lobes down here, let me try to draw with my pen. This is just showing around that nucleus. This side is going out. The bottom's going out. The red is coming in like this, just like this picture up here. So this red was coming in, this red was coming in, and the green is going out. And then sometime later, they swap directions. And so this is the harmonic motion of a sphere. So it's doing this. And that's why we draw the d orbitals the way we draw them. And of course, this is what's going on with all of these different orbitals. We just typically use 2 different colors. It doesn't have to be red and green. And those are the deformations of those shells. Now, some of them are quite strange, like these ones in the middle. Okay, these are all along the z-axis. And these out here on the ends are all along the x and y axes. And so these are the different orbital shapes. Now we have in the ground state atoms up through f orbitals, but there are g and h and I and j. It keeps going up. So it's just higher angular momentum quantum numbers, and those would be excited orbitals that we see in spectroscopy. So here's again those pictures of the traditional, pictures of the p orbitals, p, x, y, and z. The d orbitals, we have the combinations of x's and y's. So here again is that pattern of x times y, where we looked at this last time, where we had this pattern of plus minus in the xy plane. Here's the xz plane, that plus minus pattern. And so whenever we're assigning Millikan symmetries, we look at that pattern and we go, aha, I see that plus minus, that's one of those axes times another axis. And so we look to see which axes are participating in this. And this is in the xz plane. So we see that plus minus is in that xz plane. Nothing is going in the y direction, really. It's all in this x and z. And so that's the dxz. And then we look at the character table and we find xz in the character table, and that's the symmetry of that orbital. So this is really helpful to assign that symmetry. And then when you see this dz squared, they've kind of gotten lazy and just called it z squared, when really this orbital picture comes from this 2z squared minus x squared minus y squared. Yeah?
So you said that there's really nothing going in the y direction, but it looks like the bottom 2 there.
Yeah, but it's
going in the y. It looks like there's something there. Like
so if I were to cut this, if I were to cut this right here, you would see, you'd see, stuff going into the y direction really. But there's a node. There's no change in the y direction. This pattern really comes from that I guess it has the same symmetry as that x-axis, where let's say this is positive x and this is positive z, and this is minus x and minus z. And so this has that same pattern as if the axes were multiplied by each other. So this is a function of x and z that is equal to x times z.
Actually, I was talking about the bottom 2. The 2 bottom left, especially that one right there.
This one here?
The pointer on down.
Oh, no, this is a different orbital. Yeah, okay. So this one is the dx squared minus y squared. So if you were, again, this is positive x and negative x, let's just say that. And if I squared the x-axis, this would be positive here and positive there. So both the minus x values, if I squared them, would be positive. And then the y values, if they're squared, they would be positive and positive. But if I subtract them here, that makes them negative. So this would be negative and negative. And don't be bothered that up here the green ones are positive and down here the yellow ones are positive. It just, within a particular orbital, you have to be consistent. But you don't have to be consistent between the two ones. So this is x squared minus y squared. Since the y values both have the same color, that's y squared. And since the x values have the same color, that's x squared. And since they're different sign, you have that minus sign. They're different color, they have a minus sign. So this is what you would get with those lobes along the axes. Notice the axis goes right through that lobe here and here. So that's how you tell the difference between this one and the dxy. See here, this is x times y. And notice the axes go between the lobes. But otherwise, they look very similar because they're in the same plane. They're in the xy plane. So if those axes go through those lobes, like down here, then that's the x squared minus y squared orbital. And you would find that on the character table. You would see that in a particular point group character table, and you would pick that for the d orbitals. Let's say we were looking at d orbitals and we wanted to do selection rules. Is this d orbital to that d orbital allowed? Well, we need to find the symmetries of those orbitals. And so we go find the dx squared minus y squared orbital in the character table, and that's the symmetry. And then maybe we're going to an s orbital, and that's top row. And so then you figure out what light can get you from there to there. So it's really helpful that they put the symmetries of these orbitals in the labels. And same with p, x, y, and z. So this is going to be wherever in the character table, that's going to be x, y, and z in the character table. The f orbitals are not listed because they're really complicated. So we'll get you through d orbitals and that's about it, okay? We are going to do f orbital selection rules. I've never seen it myself, so I don't know how I could teach you. Now, for the hydrogenic orbitals, we don't have any energy difference between the s and the p and the d orbitals, but we do in multi-electron orbitals. So notice how in the hydrogenic system, the 2p was the same energy as the 2s, but when we have multi-electron atoms here, then the 2p is higher. And so now there's an order in which we fill these. So if we have something with, let's just look at, let's do krypton. Let's go way up high, okay? So can someone tell me, because I'm at an angle here, how many protons krypton has? 36. So a neutral krypton has 36 electrons. So you can look at that and know how many electrons you have. So let's just start adding them in here. 1, 2, 3, 4. Now, when we get to the p orbitals, we put them in one at a time like this. Okay, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, so where are we at 25? Look up there. Manganese. So this would be manganese. 25, okay. 26, 27, 28, 29, 30. And then look, we don't go to the s orbital yet. We do the 4p. 31, 32, 33, 34, 35, 36. So that's krypton. Do you see the ordering that we're filling them? We're filling them in energy order. So that's why we have this filling scheme in the order in which we fill them. Notice that we did 3s, 3p, and the next energy was the 4s. So after we got past row 3 at argon, okay, we didn't go to the 3ds, we went to the 4s. So over here at potassium, this was potassium here and calcium. And then we have the 3ds. So scandium all the way through zinc is right here, these d orbitals. So we're filling those d orbitals. So that row from scandium all the way over to zinc are the 3d electrons. And then we go to 4p with aluminum, no, with gallium and get over to krypton. So this filling scheme is based on energy, and we're just building the electron cloud up one electron at a time. And so that's practice, practice, practice. So we'll practice some today on this. And this is a nice little tool for remembering those patterns. You can use the periodic table, but you just got to know that that first d orbital is a 3d, not a 4d. Okay, so it's on the fourth row, but it's the 3d orbitals. Okay, and then the f orbitals come in there on the sixth row, but it's the 4f. That's the first f. And so you just have to remember those two things. It's the 3d is the first set of d orbitals, and the 4f is the first set of f orbitals. And if you can remember that, you can use the periodic table. And that's you got that tool right there on the test. And anytime you're doing chemistry, you better have a periodic table. Otherwise, you can use this nice little scheme. I don't exactly know why this little trick works, but it does. You just follow these arrows, and you fill the electrons in order of these arrows. So the 1s, and you come back here and go to the 2s, then you come back here to the 2p. All this is straightforward, 3s, but then you get to here 3p, then it goes to 4s. So that's that, inserting that 4s in between the 3p and the 3d. So after the 4s, then you fill the 3d, then you do the 4p, and then you're at the 5s. And then the next D group is the 4D group. That's starting with yttrium, the Y there, number 39. And so this is a nice little tool you can use. And a lot of people draw this on the test right when they get it so they can use it. Okay, or you can learn how to use the periodic table. So krypton was pretty long. I mean, that was 36 electrons. To write that out, we would write 1s2, 2s2, 2p6, and then the next one is 3s2, and then 3p6, and then 4s2, and then it was the 3d10, and then we got to the 4p, and we had 6 in there because it was a noble gas. Okay, so that's the full electron configuration for krypton. Now, that's a whole lot of stuff that doesn't change. And so we could just go back to this latest filled p orbital. Every time we have a p6, that's a noble gas. So what is the noble gas associated with this up to here? Yeah, you just go back to the previous noble gas. To see krypton, you go back to argon, and you can write that like this. So we have the argon core. And then we come into the periodic table. Now, how do I know where to start? Look, I go to argon, and then that period 4 tells us it's the 4s. So you can just come right to that. It's the 4s, and so we can start here with the 4s2, 3d10, 4p6. So it's pretty simple for all your standard elements, okay? Now, we do have some exceptions. So here's chromium. So if we look at chromium, it's the fourth element in the D block. And half-filled subshells are stable. If you think about half-filled subshells, what makes it stable is that every electron has an independent orbital and can see the nucleus. And if you look at this in chromium, we have a 4s2. I mean, fully filled subshells are stable too, because the electrons that electron correlation has some role to play in a fully filled subshell. But if we were to move that 4s electron over to the d orbital, we'd have a half-filled d shell and a half-filled s shell. So we have two half-filled shells compared to a fully filled shell and then nothing really particularly interesting with a d4. Okay, so if we can get two half-filled subshells, that's wonderful. Okay, so chromium actually drops in energy if that s electron drops over into a d orbital, and then everything drops. That's another thing that is a property of atoms, is that the energy of the atom depends upon the electron configuration to some degree. So if you move these electrons around, the atom's going to try everything, and it's going to pick the lowest energy. And so we're looking at chromium when we say, well, that's strange. Chromium has a lower energy than we would have predicted, and you look at it and you say, oh, I see what happened. An electron jumped into the d orbital, and now we have two half-filled subshells. And all of those electrons are not sharing an orbital with another electron that they don't like. So they have their own independent view of the nucleus. Now we'll look at the evidence for that in a minute, but this is then the chromium electron configuration. It's that, not argon 4s2 3d4. So if you were to look at the periodic table, it would look like 4s2 3d4. But you've got to remember that chromium is an exception to that rule, and it's going to pull that S up to the Ds, and you'll have 4s1 3d5. And so you see 3d5, that's like magic. Okay, I got a half-filled subshell. What about molybdenum? Same thing. So everything in that group under chromium is going to have this kind of setup. So for molybdenum, we don't have the argon core. We go back to the previous noble gas, it's the krypton core. Then we come into the periodic table on row 5, so it's the 5s1, and then which D is it? 4d5. But do you see the same pattern? ns1, n-1, d5. Okay. Now let's look at the evidence of all of these things. You know, we talk about fully filled subshells being stable, half-filled subshells being stable, alkali metals being easy to ionize and so on, because they just have one extra electron past a noble gas. And so here's all of our, I've stuck this graph in there. It's not in your notes. This is from that OpenStax book, okay? And so this kind of shows you the blocks and how on row 4 here, notice it's the 4s here, but then it drops to the 3d. That's what I was discussing earlier. Down here it gets interesting. We have the 6s, and then we have the 5d1, and then we get into the 4f1. So let's go ahead and do that one. Cerium. So we'll do Ce. So cerium is right in here after lanthanum. So the previous noble gas is xenon. Okay, so after xenon, we have the 6s. So 6s2. And then we have a strange thing. It's a 5d1. So we get one electron in the D subshell, and then we jump over to the F block. Okay, and then it's 4f1. And there's a nice chart in that OpenStax book that has all of the f orbital electron configurations and the d orbital electron configurations, and it's all fantastic. Okay. Here's the link here. But anyway, you can find it. Just Google OpenStax chemistry and go to the electron configuration section, and you'll find all of this. So let's look at the scientific evidence behind this. So these are the first ionization energies. So think about what that means. It's the first electron coming off of an atom. So we're going from a neutral atom to a cation. And we've been able to get the metals and nonmetals and everything in the gas phase in a vacuum and measure these. Hit them with X-rays or something and measure the energy at which that electron comes off. And so we've been able to calculate the first ionization energies for essentially everything in the periodic table. As long as it survives long enough for us to collect the data, then we can get the data. But a lot of the radioactive elements that have really short half-lives, we just weren't able to get. And so this is actually how the periodic table was made. So, some jokes here. And this is the copper. So along comes the 3d9 and says, I'll take one of your 4s electrons. Okay, and then there's Drake, of course. So we have these different trends, and we'll go through each one of these trends individually. So we see that the first ionization energy decreases with the size of the atom. So think about that, our particle in a box. What happens with size? Okay, the energies decrease of the system, right? And they get closer together. And so as the size of the system gets larger, the electron cloud gets more and more compressed. And the energy differences between these elements, these orbitals decreases. And not only that, but think about the first ionization energy. As you add more and more electrons out to the atom, they get further and further away from the nucleus and much easier to remove. The first ionization energy increases across the row in a periodic table. So we're going across the row in a periodic table. That means it's harder to ionize a noble gas than it is the alkali metals. Okay, and we'll see why that is. The first ionization energy is unusually high from a fully filled subshell. So that tells us the fully filled subshells are stable. They're lower in energy, so it takes a harder pull, more energy to pull that electron out of a fully filled subshell. And then they're also unusually high from a half-filled subshell. So this is the data that we see that tells us about these trends. And then it's also unusually low from a subshell with only one electron in it, or a subshell that's past, just one electron past being half-filled. And so this should tell us that the alkali metals are easy to ionize, the first D block electrons are easy to pull out, the first P electrons are easy to pull out, and then one electron past being half-filled, like oxygen. Oxygen is one electron past a P3, okay? So that P4 electron is easy to pull out. And so we'll see all of those. So here's the data. Let's look at these trends associated with the data. So the first ionization energy decreases with the size of the atom. And we can see that. You see radon is really low compared to helium. So this is a really large energy. And again, it's related to that principal quantum number. Helium is a 1s electron. And so this is the first ionization energy. We're going from the neutral to the cation. And so this is the electron configuration of the neutral atom. And yes, you can do electron configurations for cations and anions. Okay? It's just one electron less. So helium has 2 protons, it should have 2 electrons, but if it's a cation, it only has 1 electron. And so you just put a 1s1, and that's a helium cation. What about radon? Well, it's way out here. It's a 6p6, and radon cation has 6p5. Okay. And those energy levels are closer together because you've got a really large atom there. And those electrons, those 6p electrons, are way far away from the radon nucleus. Okay, the first ionization energy increases across a row in the periodic table. So that would be, say, sodium through argon. And so these are the rows in the periodic table. You see how the ionization energy increases across each of those rows. So down here we have lithium. And it's pretty easy to ionize because it has just one electron and an s orbital. And you make a lithium cation, and it has the same electron configuration as helium. It's a very stable electron configuration. So let's introduce a new term. That's isoelectronic. With helium. You see it has the same electron configuration, so we call that isoelectronic. So lithium cation is isoelectronic with helium. Rubidium cation here is isoelectronic with krypton. So you see we got one electron past krypton. If we remove that electron, then it has a super stable electron cloud like krypton. Okay. Now, why does this, in general, why does this increase? Well, what we're adding as we go across the row of the periodic table is we're adding protons to the nucleus. So those protons are going in the same spot. They're going into the nucleus. And yet we're putting electrons in different places around that nucleus. And so there's insufficient shielding by the electrons around that. So we want to put the next electron in a different orbital. Let's think of the p orbitals. So if we're looking at boron, carbon, nitrogen. So if I've got boron and I put in that p electron, it has a sort of a view this way on the x-axis. I put the next electron in carbon, a view along this axis. So the first electron in the p orbital sees another proton now because we're in carbon, and it gets sucked in. and the next electron isn't repelled by that electron because it's on a different axis. And so that electron is sucked in for carbon. And then we put in nitrogen, and it's on the z-axis, and it's not shielded by the first p or the second p. And so all of those electrons get sucked in as we add more and more protons. So the reason the ionization energy increases as we go across a row is because we have insufficient shielding by each electron. And so all of the electrons can feel more and more protons, and they get sucked in closer and closer, and it's harder and harder to ionize them. And so that's another reason why that noble gas is super stable, because we have sort of the perfect arrangement of electrons around that nucleus where all of them can interact with each other and interact with the nucleus in all different directions. And then we add one more proton and put an electron in the next shell. And it's so much further away from the nucleus, it's a noble gas, it's easy to kick that electron out and get back to that stable noble gas electron configuration. Even more stable now because it has another proton thrown in. So that's why the alkali metals are so easy to ionize. Those electrons come off very, very easily. Okay, and up here, the neon going to neon cation. Here we have a super stable noble gas electron configuration, and we're going to wreck it. It's really hard to do. It's hard to pull that sixth electron off because it's a super stable nucleus. In fact, you could say that their neon should be here, but when we get that stable electron cloud, it actually kind of drops in energy and makes this ionization energy larger than you would expect. It's just really, there's a big jump here between these two. And so that tells us that fully filled subshells are stable, more stable than we expect. And so this is also what we see with the noble gases, these fully filled subshells, but also the s orbitals too. Those are, notice this little glitch. So lithium, and then it goes to beryllium, and then boron. So this beryllium is a little higher than we expect, and sodium going over to magnesium. Magnesium is a little higher than we expect. Look at aluminum here. So what's going on here? Well, this beryllium and magnesium have fully filled s subshells, and so they're a little higher than we would expect. And the same with the zinc and cadmium; those are fully filled d subshells, and they're a little bit higher than we expect. And mercury is a fully filled d. So that beryllium has a stable fully filled subshell, an S2. And so again, if the neutral is stable, we've made this difference, this big black arrow, a lot longer than we would expect, because the neutral was stabilized. Whereas boron, it's one electron past a filled subshell. So if we can get rid of that electron, we have this beautiful filled subshell. And so there the cation has been stabilized. And so this energy difference is a little closer. And so that makes that ionization energy a little smaller for boron. Same thing for aluminum. And then way over here, this neon, again, we don't want to wreck that beautiful noble gas electron configuration of a 2p6. And so this the neutral was stabilized. So if the neutral has a stable electron configuration, then the ionization potential is going to be much higher than we expect. Now, we also see this effect in the half-filled subshells. So this half-filled subshell would be nitrogen, and below it would be phosphorus. So notice there's also that little glitch of oxygen being easier to ionize than nitrogen. And that's because the nitrogen is unusually high in terms of its ionization potential, and oxygen's unusually low. So here we have that half-filled subshell, the 2p3, and so that means that the neutral has been stabilized a little bit because it's half-filled. That makes the black arrow longer than we expect. Whereas in oxygen, the cation has the 2p3, and so the cation has been stabilized. And if you stabilize the cation, then that black arrow is shorter than you expect, and so it's easier to ionize. So all of these trends that we see in the ionization energies are where we get these rules for our electron configurations, and why we say half-filled subshells are stable. You know, it's the data that tells us that. We didn't just come up with it. And so then, naturally, if those fully filled subshells and half-filled subshells are stable, then when you go one electron past those, then you're going to see an unusually low first ionization energy. And so for this boron, we've got that extra electron. It's one electron past a fully filled subshell. And so this cation has got the stable electron configuration. And so since that's been stabilized, that's a really short black arrow, which is the ionization energy. And then the oxygen has gone one electron past a half-filled subshell. And so here the half-filled subshell stabilizes the cation, and that makes that black arrow shorter. And then same with lithium, it's just more of the same. Okay. Now let's look at the comparing this to the Grotrian diagram. This is another trend added in from past set of notes, and that is whenever you have an ionization occur in a D block or an F block element, it's the s orbital that typically donates its electron. So if we're looking at that one, we had chromium, and it's a 4s1 3d5, and we're going to make a chromium +1 cation. Where does the electron come from? Does it come from the d orbital or the s orbital? And in general, it comes from the s orbitals. Okay, so if you get the chromium cation, it would just be 3d5. There wouldn't be any s electrons. And so we see that right here in these d blocks, and then the f and d blocks here. And you can see that in the Grotrian diagram for mercury, which we're going to talk about. It has the 4f14, the 5d10, and then notice all of the things that change are those s electrons. We have an s electron hopping around in the p orbitals here, but then here's what we would say is the ground state configuration for mercury: 6s2, 5d10, 4f14, and those s electrons are the ones that are mobile. They can jump up to the 7s. They can jump into a p orbital, and in fact, putting it in the p orbital actually drops its energy. So we wouldn't know that without actually going to the atomic spectral database and finding that out. But it's that electron that comes off. So right here, once you get past this ionization limit, then up here we have mercury that's ionized. And so that has the xenon xenon core, 4f14. It really doesn't matter that these are in a different order than the alphabet filling scheme. We're just writing them 4, 5, and 6. 5d10. And then now this has a 6s1, right? Whereas in the neutral, we would have written this: 4f14, 5d10, 6s2. Okay, so it was that s electron that got ionized. And I wrote it out by hand, and there it is, nicely printed. Okay. There, so you can read it. All right. So let's practice some more electron configurations. So let me go ahead and I can just do this, use this white space here. So someone pick an element that we want to do. I know, let's look at the ones in OpenStax. Let's do that. Let me go back to that and click the link. Here we go. Okay, let me turn on the browser. There, this is the figure that I want. Okay. browser. Let's see. Yeah, all right. So in that OpenStax book, we can see, even in these D blocks, all of these different elements. So for like yttrium, that's 5s2, 4d1, then zirconium, d2, and then niobium, we're getting close to that that d5, and it actually pulls one up and makes a 5s1, 4d4, and then molybdenum is just like chromium, 5s1, 4d5. And it stays 5s1 all the way up here until we get to palladium, and palladium has pulled all the electrons up, so it's 4d10. And then silver wants that d10, so it puts an electron in 5s1, 4d10, and then cadmium has both of them filled, 5s2, 4d10. So you can go through here and you can see all of the ground state electron configurations for all of these different atoms on the periodic table. So check your work with this diagram here in the OpenStax book. And once you are good with the electron configurations, then you'll have a good chance of doing the term symbols and getting everything correct. But we've got to be good at doing electron configurations before we head into term symbols, which is coming up next. Okay, so I'll give you some time to practice. All right, take care. We'll end early.